Welcome to this last session of ICNP 2020. Welcome especially to the speakers, and welcome to everybody who has come to attend this session. Maybe this is the thing, you can also attend the sessions. It's not the last one if you're not actually physically there, right? So let's see. So we have three very nice papers about wireless. I think they're very different from just pure protocol things. Let's start. So as I said, I don't know if everybody was already online. I will introduce the speaker, of course, and they have the talk, and then we do the Q&A here live. And if you want to ask questions, just raise your hand. And then turn on the camera while you are asking the question and while you are interacting with the speaker, so that this becomes a bit more lively and not so lonely. Okay, so let's start with CSIscan, learning CSI for efficient AP discovery in dense Wi-Fi networks. This is a talk by Kunal Sankhe, who is an engineer at Qualcomm, right, doing your Ph.D. in using deep learning for wireless, right? I didn't exchange you with anybody else. So, so go ahead, share your screen and present. You have 20 minutes and we'll go to the Q&A.
Sure. Thank you, Anna. So let me know if you can see my screen. Can you see my screen, Anna?
Yes, I can.
Okay, so I'll start. Hi, everyone. I'm Kunal Sankhe, and today I'll talk about our work, CSIscan, which is an efficient way of discovering access point in dense Wi-Fi network. So this is a joint work with my colleague Dheryta and my advisor, Professor Kaushik Chowdhury. This is the outline of my talk. So in today's world, we know that Wi-Fi is no longer a luxury. It is our common expectation to have a Wi-Fi connection. We use Wi-Fi not only at our home or offices, but also while shopping at shopping mall or at even subway station, or probably even at stadiums. Now imagine that you're walking inside the stadium and there is a Wi-Fi connection available. The first thing that you will do to access Wi-Fi is to search for all available access points. Now, this process of searching an access point is called AP discovery. Now, along with you, there are thousands of spectators who are trying to access, who are trying to find the access point. Now, this simple process of searching an access point causes a huge overhead on the Wi-Fi network. And therefore, this AP discovery is said to be an Achilles heel for Wi-Fi. And this is especially true for dense Wi-Fi network. Now, to provide real-world evidence of the problem which is caused by AP discovery, we conducted two studies. In the first study, we tried to analyze what is the spectrum wastage that happens because of the exchange of discovery packets. Now, for that, we collected Wi-Fi traces in our student cafeteria, where around 100 to 120 students were present, and they were accessing Wi-Fi using their laptops or smartphones. Now, we collected traffic in two bands for around 30 to 35 minutes. And we were mainly interested to capture traffic which are associated with AP discovery process. So in this case, the probe request and probe response. In the second experiment, we wanted to analyze what is the impact of discovery on Wi-Fi latency. Now, what is Wi-Fi latency? It is the latency between the client and the last hop connected access point. So in our experiment, we had a Wi-Fi which was connected to Wi-Fi hotspot server, and to measure time, we relied on the ping utility. So in this case, we measure round trip time, which symbolizes very similar to Wi-Fi latency. Now, while doing this experiment, we made sure that the client is actively trying to search all the available access points. So it was triggering an AP discovery process after every 2 minutes. We also made sure that all the background traffic is disabled to get the realistic measurements. Now, let's try to understand what is the impact of active discovery in terms of spectrum wastage. Now, probably this looks very complex diagram, but let me simplify it. for you. So we have a Wi-Fi client, which is trying to discover access point. There are multiple access points in the network. Now, let's imagine that these are the group of APs which are operating on channel number X. Now, this client, to search for an access point, what it does, it sends a packet, a special management packet called probe request. After sending probe request, it waits for a time. This time is called minimum channel time. This is usually a time to simply sense a channel. If it finds any kind of activity on that channel, it will wait for a time called maximum channel time. So during this time, there could be multiple APs who responds to this probe request with probe responses. Now, after max channel time, basically client switches to discover APs on the next channel. Let's say in this case, X plus one. So now this process is called active discovery. And probably you may also recollect that there is other type of discovery called passive discovery, which simply relies on the beacon packets. But usually the client follows more active discovery than the passive discovery. So the problems which are associated with active discovery are more important to investigate. So here we focus mainly on active discovery. So as I said earlier, so this is the active discovery. And as you can see, there could be multiple retry frames. Now, what is retry frames? So whenever access points send the probe response, it expects that the client will respond back with the acknowledgement. So if the AP did not get any acknowledgement, it will try to simply resend these probe responses. And these are the retry frames. In our captured traffic, what we found that around 75% probe responses were retry frames. So now imagine that these retry frames are trying to congest the network. The other issue that we found that some of the probe responses were sent after the max channel of the time. So the client, which was earlier operating on channel number X, is already moved on to channel number X plus one. And the APs are still trying to send the probe responses. Now, both the retry frames and the frames which are sent after max channel time are simply redundant for the client because they are not useful for this client to discover APs. And in our particular case, we found around 62% probe responses reach after max channel time. Now, the question is, how to minimize this number of redundant probe responses. Now, why this is important? Because these probe responses are sent at the lowest order of modulation scheme, probably BPSK or QPSK. So they consume a lot of spectrum airtime, and this results in the spectrum wastage. And this is not something new. A lot of people in the literature have stated this issue. So these are the references you can find. Now, the next problem that we found was with respect to Wi-Fi latency. So as we collected Wi-Fi latency with the ping utility, what we found that whenever client triggers active discovery, the latency shoots up from, let's say, 5 millisecond to up to 150 millisecond, and we have seen that it also lasts for few seconds later. So on the right hand side, we tried to learn its distribution. So we plotted CDF, and in this case, we plot two things. One is when the client actively scans the network is called periodic active discovery, and when there is no active discovery trigger. Now, in this case, we can see that the median value of this latency is very similar. It's around 5 to 7 milliseconds. But what we observe that there is a long tail distribution. What does it mean? That 90 to 97 percentile value is very high as 150 millisecond delay. Now, why this is important? It has been studied in the literature that this kind of distribution where we observe long tail Wi-Fi latency, it could be around even 25 milliseconds. That causes an application level of delays, and these delays can result into a page load, and it could be as high as 2 to 3 seconds. Again, this kind of page load delay is very bad for the customer. If we observe that there are websites which are very slow to load, we will simply don't use those websites. Also, for the companies like Amazon, Facebook, they actually there is a monetary loss for those companies. So this is an important issue for them as well. So these are the two problems which were associated, and we try to analyze, especially related to active discovery. Now, again, question is how we are going to minimize this latency which is caused by active discovery. And to overcome these problems, we try to design the new approach, which is called CSIscan, and this is our vision. So this is very similar diagram as we seen earlier, but now what happened? The client, instead of searching access point across all the channel, what it does, it expects some kind of information from the access point. Now, what does it access point does? This access point, whenever they are communicating with other client, they also encode some kind of discovery information. Now this discovery information is leveraged by this Wi-Fi client, which wish to discover APs, and across all the channel, it simply processes physical layer frame, and within that also only CSI to extract discovery information. Now just to emphasize, the client always processes all the physical layer frames, uh, and at the MAC layer it decides whether to discard those physical layer frame or use that for the further processing. So this is not something we emphasize the client to do. The client already is doing that. Now after processing all the channel and extracting discovery information across all the channel, it try to find one particular better channel, let's say best channel or the better channel among all these channel, and only on that channel it simply follows the regular AP discovery process. So this is very simple. Now you may ask, how does AP encode the information? How the client discovers, decode this discovery information? And that is what CSI scan contribution is. So just to recap, what is CSI? This is what our major focus is. So before we jump into, let's try to understand what is CSI. So as we know, CSI is represented into two things. One is magnitude and the phase plot. Across x-axis, we have the subcarrier index. In this case, there are 52 subcarriers. Usually if we have a 50 size of 64, we use only 52 subcarriers. In our case, we don't usually rely on the magnitude plot, so we will only concern about the CSI phase plot. We also do two kinds of post-processing. The first post-processing is called unwrapping. So as we know that the phase is usually wrapped between minus 180 degree to 180 degree. And here we have a discontinuity. Now to remove this discontinuity, we do some kind of manipulation of adding 2 pi and minus 2 pi. And by doing that, we get very linear straight line. So this is the first post-processing that we do. After that, subsequently, we do another post-processing, which is called detrending. So it's simple that we just basically remove the slope of this line and bring it to 0 degree. So here we have a very approximately linear line around 0 degree. So these are the two post-processing steps that we do. Now how does AP uses LTF and the client uses LTF to estimate the CSI? So on the left hand side, we have a sequence of X of K, which is in the frequency domain. This is the sequence which access point uses. This is a fixed sequence. This is the frequency which is used, and this is in the frequency domain. So after OFDM, after IFFT, we get a time domain sequence, and this time domain sequence is called legacy long training field. So this is the field which is a part of the Wi-Fi preamble, and this Wi-Fi preamble is used by the client for the channel estimation. So as we have seen on the right hand side, the client has plotted, we have this CSI. So on the right hand side, we have a CSI phase information, and on the bottom, we have process CSI phase, and these processes includes unwrapping and detrending operation. So now let's imagine that we have the same sequence X of K on the left hand side. Now let's say there is one field which is one value, and we add a deliberate phase distortion of 40 degree. So instead of using value 1, let's say we use a complex number. So now what is the effect on the CSI? So we see there is a jump in the phase shift. So the effect of distortion at the AP side is visible in the CSI at the client side. And this effect is also channel independent. For the different channel distribution, we still see the similar phenomena in the process CSI phase. Now this effect is, so there are two information which are important here. Now, what is the subcarrier index which is used, where exactly the modification has been done. So here, as we did modification in the subcarrier index minus 16, so we see similar effect at subcarrier index 16, and how much phase distortion was added. So here we can see around 30 to 35 to 40 degree of phase shift. And the question is, can we introduce phase distortion in more than one subcarrier? The answer is yes. We can also introduce phase distortions in more than one subcarrier. So what we are doing here, we are intentionally modifying the LLTF at the access point, and those effects are visible at the client side in the process CSI. Now, how do we use this? How do we leverage this to encode some kind of meaningful information? So now let's say we have this sequence X of K, we divide it into several groups, and let's say we focused on only on one group. Now, in that particular group, we have, let's say we have two mapping table. In the first mapping table, there are different phase distortion, different level of phase distortion. On the right hand side, we have the index mapping table, which decide which subcarrier index was modified. So let's say we are trying to modify, or we are trying to add the phase distortion in the 0th subcarrier index, and we have a choice of introducing different level of phase distortion. So in a way, that we can also add the similar phase distortion at different subcarrier index. So now the total number of bits that can be stuffed only in this particular group is defined, is can be evaluated by this formula. So now just to take an example, if L is 1, let's L is the number of indexes where we introduce the phase distortion, and we have a choice of 4 levels of phase distortion. In this particular example, we can carry 3 plus 2 bits of information. So overall 5 bits per group, and we have total 6 group. We can carry 30 bits of information per Wi-Fi packet. So this is the way of encoding information by deliberately or intentionally adding the phase distortion in the LLTF field. From the decoding side, let's say this is an example of the encoding on the left hand side. For the decoding, we can simply, so this is the CSI, process CSI phase at the client side. We can simply divide into different thresholds and determine determine where exactly the phase distortion is added and how much distortion is added. And we can use, the client can use similar phase and the index mapping table to decode this information. So this is just an example of it. So here at subcarrier index 19, we introduce phase distortion of 20 degree, and we can see a similar phase distortion at subcarrier index 19. We observe around 21 degree of phase distortion. So this is an example of CSIscan decoding. Now imagine that as we introduce the phase distortion in number of subcarriers, we try to evaluate what is the impact on the packet error rate. I think many people would have this question. So that's why we evaluated in a simulation what is the impact, and we observe that as we increase the number of subcarriers where we introduce phase distortion, the packet error rate increases. This is also true as we increase the level of phase distortion. This is also true as we increase the MCS value of the packet. So for example, if we use QPSK over 16 QAM, the packet error rate is going to increase. Now just to keep packet error rate within some threshold, we can opt for decide that the number of subcarriers is 1 and the level is 1. Like we can minimize the packet error rate, but this will allow us to transmit only 3 bits per packet. Now this is not optimum to transmit any kind of meaningful discovery information. So we need to to improve the data rate, to improve the number of bits that we can stuff. We'll have to find some upper bound on n and theta. Here n is the number of subcarriers and theta is the maximum phase distortion that we can add. So we have to select this value dynamically so that the packet error rate will always be within some threshold. Now to do that, we try to use machine learning. So how does this machine learning operation work? So let's say we have access point, and there are 2 types of the client: associated client and the discovery client. So I just to recollect that we are leveraging the communication with associated client to send an information for this discovery client. So for that, we rely on the previous transmission from this associated client, and we estimate the CSI and the SNR. So this will give us what is the channel quality for that particular link. Also, for the next outgoing packet, which is intended for this associated client, what is the MCS value which is used? And then we use a machine learning approach to decide to determine what is the optimum level of n and theta. And we, in this case, we try to use CNN. And these were the four classes that we use in our particular class. Of course, these we can have different choices, but these are the choices that we choose to select in the CSI scan. So basically, CSI classifier will decide one of these classes, and once we know what is the level of n and theta, we can use CSI scan encoding block to modify intentionally the LLTF field, and that will be our next outgoing packet, which is intended for associated client, but also leveraged by discovery client to extract the discovery bits. So this is the overall operation of the CSI scan. So this is the convolution architecture that we use. I won't go through the detail. This is very simple architecture, and so our novelty is not designing in the architecture, but the way we have used and the way we have designed, the way we have designed the input and the output. Our main contribution was using supervised domain adaptation. Why? Because we decided that to capture traffic in a real environment is really painful. We also, once we capture traffic in one environment, it's not useful in other environment because the environment has changed. And for that, we try to use the simulation environment we have, where we have the with limited effort, we are able to capture a lot of traffic, and to train neural network, we required a lot of traffic. So we try to train the neural network with the data collected in a simulation environment. But to work this in a real environment, we had to use some kind of domain adaptation technique. In this case, we use supervised domain adaptation technique. In that particular, we use fine-tuning approach where we froze the neural net, only the convolution layer, where we observe that this convolution layer is able to learn the parameters, learn the specific features, and which is basically learned by the data collected in a simulation environment. And for real test bed, we use this fine-tuning approach for domain adaptation. Now let's go through the performance evaluation section. So this was our experimental setup. We had associated and the discovery client. So just to compare with the traditional active discovery, so active discovery protocol, actually it scans all the 39 available channels. So including 2.4 and the 5 gigahertz. On the other hand, our CSI scan only scans one channel. Now, in our case, we decided to channel one particular channel upon successful decoding of the information bit. If it is not able to decode this information, it scans all the 39 channels like active discovery. So this was our performance comparison protocol. What we did was, our discovery information is encoded in every traffic that was intended for the associated client. So this is kind of way of aggressive discovery protocol. So we wanted to analyze what is the worst case performance, and we tried to use this below metrics. One is how many number of probe responses generated per probe request, what is the latency. Also, we try to analyze what is the CNN accuracy, and how much bits we could actually stuff inside the packet on average, and what is the packet error rate. This was our deployment scenario. We considered three cases, where in first cases we had stationary and line of sight associated as well as discovery client. In second case, our clients were non line of sight from the AP. And for the third case, we wanted to evaluate with the realistic scenario where both the clients were moving. So this is our evaluation. As we see that the left-hand side plot, we try to analyze the distribution of number of probe responses. What we observe that the number of probe responses which is generated per probe request on average has reduced from 22 to 6. So overall, it reduces the probe response by 72%. So this will help to save the spectrum over airtime, and in a way it will reduce the spectrum wastage. For the second case, we try to observe what is the long tail, whether we observe any kind of long tail distribution. And in that case, we observe that the 99th percentile value was reduced from 132 to 6 milliseconds. And for the CNN accuracy, with the simulation data, we got accuracy around 95%, where we use 80,000 example. On the other hand, for a live environment, we were able to get very similar accuracy of 93%. The real benefit was we only used 12,000 training examples. Now this is an bit stuffing efficiency plot. On the left hand side, we try to compare how many discovery bits were stuffed per packet on average, and on the x-axis we have different MCS rate modulation schemes. We compared with different approaches. The first approach is overly pessimistic approach, that using always the low value of n and theta. Other is overly optimistic approach, always go with the high value of n and theta. Moderate is like the moderate value, and the CSIscan basically dynamically select the optimum value of n and theta. Now, what we observe that I think I'm.
Ask you to wrap up.
Yeah. So let me summarize this slide. So basically, we try to compare the bit stuffing efficiency with the CSIscan with other three approaches, and we observe that CSIscan is able to stuff very high bit stuffing efficiency, very close to optimistic approach, but is still able to maintain very low value of packet error rate. Just to summarize, this is novel AP discovery method, and our contribution was how we encode discovery information and how do we decode it. Also, we designed CSI to learn the optimal level of n and theta. Also, of course, we developed the proof of concept as well with the USRP, AP, and the client. And these are some results that we found. Thank you. So you can ask questions if you have.